Hey, good morning, everybody. Yesterday, you did a 29-minute problem on PV diagrams and the quantitative analysis of the first law of thermodynamics. If that doesn't sound impressive, then I got nothing. I think after last class, we need to backtrack a little bit, and we really got to focus in on the signs. If you could dig this sheet out in your packet, we're going to fill this out and then hopefully do example number 2 today. But I think in order to really fully get that, we need some musical background. Because I think when it comes to thermo, it's not all that hard, actually. I think the real key is that you got to get the signs right, if it's positive or negative. When work is done on the gas, that's right, that sign would be positive. And when when the gas does work, that would be negative because it's going to take away from the internal energy of the gas. Is anybody listening at all? I don't think so either. I'm going to turn this down a little bit. And maybe we can get working on those signs. All right. So I took the liberty of writing down a few of the formulas. I can, I don't think I can teach while this is on. You can look it up later. It's pretty funny. That's a good one. Here. I took the liberty of writing down some of the formulas ahead of time. So if we start up at the very top, write it down, it'll help. We have change in U equals Q plus W, known as the first law of thermodynamics. We have work equals negative P delta V. We're going to look at that when it's an isobaric process, so it's a straight line across, and we can find the area under that curve, because it's not a curve, it's a rectangle. And then the internal energy of a gas can be calculated a few different ways. We have 3 halves PV, 3 halves nRT, and the change in energy would just be the final energy minus the initial. So in a process from A to B, you would take the energy at B minus the energy at A. That's it. All right, so what do you say we fill in some signs? They're everywhere. Clogging up the scenery. Now, I also drew in a picture of a PV diagram with isotherms. And the key is underneath that volume axis to picture a piston. If you picture a piston, when it goes to the right, the gas would be expanding and pushing out on something. When it's compressed, the piston would move to the left, and something would have to be compressing it. All right, cool. Let's look at the signs. So, isothermal. We're not going to fill in every square at the top, but the ones we know we can. For an isothermal process, the change in temperature is going to be what? Right, 0. Good. Can we say anything else? Well, if it's isothermal and there's no change in the temperature, then there has to be no change in the internal energy. Because the internal energy of a gas is 3 halves nRT. Now, some of you are thinking, well, wait a minute. What if P and V didn't change? Can't happen. You can't have it be isothermal and not have a change in the product of PV. Actually, strike that. Rewind it. Now skip over it. Adiabatic. Adiabatic says that the heat has no chance to flow. So whether it's compression or expansion, adiabatic means that Q is 0. Okay? So Q is 0. And lastly, isobaric, we can find the work is equal to negative P delta V. Got it? All right, so let's go through down below whether or not a process will be called positive or negative based on this isothermal expansion or compression. Now look, these are the 4 graphs I would like you to draw in. If you have a PV diagram and it's isothermal, it's going to follow one of those isotherms. Temperature wouldn't change. For adiabatic, adiabatic actually jumps from one isotherm to another. And some of you are going to be worried, like, how do I draw that curve right? You don't worry about it. I'll explain in a little bit how you know if the temperature increases or decreases. Isometric, the volume doesn't change, so it's going to be a vertical line. Can you find the area under that vertical line? What would it be? That's right, 0. And isobaric would be a horizontal line. Okay, good. Thanks. Now let's talk about these. Positive or negative? Isothermal expansion. What's the change in temperature going to be? It's going to be 0, so the change in internal energy is also going to be 0. Now it's expansion. If it's expanding, that means that the piston is pushing out. So the work done on the gas is negative. Expansion means the work done on the gas is negative. Okay. Now, if you go to the first law of thermodynamics, if the change in internal energy is 0 and the work is negative, what's the heat have to be? Yeah, positive. Heat had to have been added to the system. Good. Now, for isothermal expansion, the change in pressure, let's think about that. As it expands, let's look at the graph. As it expands, the pressure is going to go down while the volume is going to increase. Okay, isothermal compression. Again, isothermal, so we've got 0 and 0. When it's compression, we would say that the work is positive on the gas, so heat would be negative. A negative heat means that heat flowed out of the system. Flowed? No, flowed. Flowed, yeah, flowed out of the system. Because it's compression, the change in volume would be negative, and the pressure would increase, so that would be positive. Adiabatic expansion. Now, adiabatic expansion means Q is going to be 0. Expansion means the volume increases. So what's going to happen to the pressure? It's going to decrease. But what about Q and work? Well, I know that work, if I go back, I'm going back right over here again. In adiabatic expansion, if it's expansion, then the gas has negative work done on it. Essentially, the gas is doing work onto something, which means it's going to take away from the internal energy. So the internal energy there is going to be negative. If the internal energy is negative, then what has to happen to the temperature? The temperature must have dropped. Now, I got a quick demo for that. I actually went into school on Friday, and I got Mr. Croto to come in and be our guest. And here we had a quick demonstration for you. So I'm going to, hopefully this doesn't get all glitchy on you. Oh.
And unfortunately, you can't be here, but you know who can be? Mr. Croto. There he is. Mr. Croto. Right, Mr. Croto right there. He's going to stand in for Sam today. And you'll notice he's apparently barefoot in school, and he's got the cinch going on as well. Adiabatic expansion. Best example I can come up with for adiabatic expansion is what happens with a fire extinguisher. Now,
don't do this at home.
Fire extinguisher under pressure. It's under pressure. So as it expands rapidly, what will happen is heat will not be able to flow into the gas in order to increase its temperature. So you know what's going to happen? There's going to be a drop in temperature, a dramatic drop in temperature, because no heat is allowed to flow. So it's adiabatic expansion. The only thing Croto's going to do is tell us if it's hot or cold. Got it? Are you ready?
No.
So now oh wait, no, I'm not going to shoot it at his head.
That would be dangerous.
Oh, God, that would be funny. All right, next time. Here we go. Ready?
Oh, that's close.
It also happens to be empty, which I did not realize when we came into the building. It was still cold. Was it? Cut. Well, that didn't work.
But
Alright, you guys, so
what happens is when a gas expands so quickly that heat doesn't have a chance to flow in, the temperature is going to drop. An expansion valve, say in a refrigerator, has the gas undergo an adiabatic expansion, and that's actually the key to a number of different processes. Here's what you got to know. When you shoot a fire extinguisher at something, you're not putting it out because it's cold, right? It's carbon dioxide, which suffocates the fire. However, because it's expanding so quickly, the temperature in the gas drops dramatically. I should have been able to get some frozen CO2 to form on the floor, but honestly, the fire extinguisher was pretty much empty. Adiabatic expansion. Expansion so it gets cold. Okay. Now, with that in mind, adiabatic compression. In adiabatic compression, the heat's still going to be zero, but the gas was compressed. So there was work done on the gas, so that would be positive. I'm doing work to the gas, so I would increase its internal energy. Because it's compression, obviously the volume is going to get smaller and the pressure is going to increase. And because it happened so fast that the internal energy increased, the temperature would increase dramatically as well. So I grabbed another demo, and this time I got Hannah to sit in for me, or sit in for you. All right, everybody. So I've got a quick demonstration of adiabatic compression. Mr. Croto is unavailable, so instead I got a better student. Hannah Edgar is going to step in his place today. What I have here is something called a fire piston, and it's got an O-ring on the end, so it forms a nice seal. Oh, that's right in front of your face here. I've got a tube here that's hollow, a piston, and on this block I've taken a match, cut the head off, and I placed it right there. Now in adiabatic compression, the key is it happens so fast that heat does not have an opportunity to flow out. And if heat doesn't flow out, Hannah, what's going to happen to the temperature?
It's going to increase.
That's right. And if that increases, then the internal energy of the gas is going to increase as well. So if we're able to do this fast enough and compress that gas down into a much smaller volume and not allow any time for heat to flow, the temperature has to increase. And if the temperature increases dramatically, we should be able to spark that match. Got it? All right. This is a 50-50 deal. We'll see how it goes. So I'm going to depress the top of the piston very rapidly, and we'll see if we can get a spark. Hannah, you good? You're going to be our witness. Here we go, Hannah. You ready? All right. What do we call this? Adiabatic compression. Ready? Set. Oh, we had it. We had it. Oh,
Yay!
That counts. That counts. Adiabatic compression. The heat did not have a chance to flow. Now if I... Got it? Now, on the graph, I have to think about that. So, adiabatic expansion, shooting Mr. Croto with a fire extinguisher, means that the volume increased so the temperature decreased. So my curve would go from a higher isotherm to a lower isotherm during adiabatic expansion. But in adiabatic compression, say when you fire a piston so quickly that the temperature increases, that's how ignition works in a diesel engine, by the way, what you would end up having happen is that the temperature would increase, so it would go up in isotherm. If you didn't get that, rewind it, watch it again. I can't do any better. I probably someone else could, but I can't do any better. Last, isobaric. Isobaric expansion. Let's talk about the signs. If it's isobaric expansion, then obviously the change in pressure would be zero. If the change in pressure is 0, does that tell us anything else? Well, because it's expansion, I know that the work is going to be negative. All right. Now, let's go down to the graph. This is tricky. If we go to isobaric down here, isobaric expansion, what has to happen to the temperature if it expands at the same pressure but the volume gets bigger? Yeah, if I go from left to right, I'm going to have a positive change in temperature. If I have a positive change in temperature, that means the internal energy of the gas had to increase. Volume would be negative because it's expansion. Now look, heat. The heat, if I somehow had the gas do work, meaning it gave up some of its energy in the form of work, and the internal energy somehow increased, then I must have had to add a lot of heat to the system, right? It's during this process that a lot of heat would have had to have been added. On the flip side, during isobaric compression, as I go from right to left, the temperature is going to decrease, meaning the change of energy is going to decrease, even though the work on the gas, because the gas is being compressed, would be positive. That means that the heat had to really flow out of the system during isobaric compression. Are you supposed to memorize all those? No? But you are supposed to understand it. Good luck. There's a lot going on here. However, you guys are very smart people. And while you won't memorize this, if you have a few ideas in your head, you should be able to piece it together. When a gas expands, it's negative work because the piston is pushing out. When a piston is compressed, then work is done on the gas. That would be positive work on the gas. All right.